Hello students. So today we people are going to study about the power of length and its derivation. So let's study about this. Question is, define power of length. Write its SI units and dimensional formula. So in the previous lecture I have also already defined it. So let's study it once again. Power of length can be defined in two ways as according to the 10th class. We people have studied, that is the reciprocal of the focal length. Reciprocal of the focal length of a length is known as its power. Reciprocal of the focal length of a length is known as its power. It is denoted by P. It is denoted by capital P and is given by P is equals to 1 by F. So in this way, as per the lower class standard, we have studied this definition, but here in the 12th class we people will define it in the another way, that is, or in the another way how we can define it, that is it is defined as tangent of the angle, by which it converges. It is defined as, that is, power of length is defined as tangent of the angle by which a length converges or diverges. The rays of light converges or diverges the rays of light to its principal focus when the rays of light are incident on it. When the rays of light are incident on it at a unit distance. So in this way we can define, again I am defining, it is defined as the tangent of the angle by which a length converges or diverges the rays of light to its principal focus when the rays of light are incident at a unit distance. That is what we call power of length. Now, in order to understand it further, let us consider a convex lens is here. A ray of light is coming from the object like as. So it is traveling parallel to principal axis, and let us consider it is made incident on the lens at a unit distance, that is h, from its optical center. Then what would happen after refraction? This ray of light will converges to its principal focus, that is f, and the distance between optical center and the principal focus is denoted by small f. Then how much this ray of light has got deviated, or what we can say converged. So this angle is delta and this angle is also delta. So here we can write power of lens is equals to tangent of angle by which the ray of light converges or diverges. And this angle is so small, so that we can write this delta is equals to h by f. And what about this h by f? H is the unit distance and f is the focal length in meters. And if we are writing the focal length in centimeter, then we can write 1 over or 100 over f when we are taking it in centimeters. So in this way we can define this power of lens. Now, what about the SI units? SI units of power of lens are diopter, or simply we can say denoted by capital D, or meter inverse. In this way we can explain about this. So this is all about the power of lens. Now, the derivation is there. What about the equivalent power of the two lenses when they are separated by small distance d? Suppose we have given the two lenses L1 and L2 and they are separated by distance small d, then what about the net power of the combination? So let us derive that expression. Here it is clear to you. Once again repeating. You can also define either of the way. Power of lens, it is defined as the reciprocal of the focal length of a lens, that is P is equal to 1 by f, or as according to the 12th class definition we can define it. It is defined as the tangent of the angle by which a lens converges or diverges the rays of light to its principal focus when the rays of light are incident at a unit distance on it. So in this way, here we have considered the convex lens, need not necessary, we can also take the concave lens. So let us consider this ray of light is falling on it at a unit distance, as a result of which, as this lens is converging lens, so ray of light after suffering refraction will passes through the principal focus. So the distance from the optical center and the focus is called focal length. So we can define this power P will be equal to tangent of angle delta, and delta, this angle is so small that is approximately equal to delta is equal to h by f, and this is equals to 1 by f. Why? Because we have considered this distance as a unit distance. So 1 by f in meter, and in centimeter, if focal length is taken in centimeter, then formula will be like that. So in SI unit, the SI unit of this power of lens is denoted by diopter, written like that, and capital D or per meter, in this way. Okay. Now we people are going to derive the formula for the net equivalent power of the two lenses when they are separated by distance capital T. So the question is like that is, expression for the power of the equivalent power of the lenses when they are lying at a distance small d, not capital D, small d. Expression for equivalent power of two lenses when separated by distance small d. Okay. So here in this case, let us consider we have the two lenses lying on the same principal axis. as shown in the figure. Let us consider this is length L1, this is the length L2, such that the length L1 has optical center C1, length L2 has optical center C2. Now, a ray of light coming from an object traveling parallel to principal axis falls on the length L1, as a result of which this ray of light suffers the refraction, since it is the converging length. So after suffering the refraction, let us consider this ray of light in the absence of length L2, it gets converged at F1, because according to the rule, the ray of light traveling parallel to the principal axis when suffers refraction from length L1, as it is converging length, so the ray of light will passes through its principal what we can say focus. So let us consider this ray of light meet at point F1, such that this distance of the length L1 from F1 is denoted by this small f1. F1 is the focal length of length L1, and consider that further we have already considered that the distance between these two lenses is small d. So we have to find the equivalent power for these two lenses. Now what would happen? In the absence of length L1, this ray of light should have gone straight. So in the presence of this length L1, this ray of light has suffered the deviation. Let us consider this angle as delta 1. Now if this angle is delta 1, then this angle will also be equal to delta 1. Further, the ray of light, let us consider it is made incident on the length L1 at point A at a distance H1 from C1, such that AC1 is equals to H1, or we can say this is the unit distance, or what we can say distance from this optical center of this ray of light. Now what would happen if this length L2 is placed at a distance D from length L1? Then this ray of light will again suffer the refraction, and instead of focusing at here, this ray of light after suffering refraction, let us consider it gets focused by the lens L2 at its principal focus denoted by F2, such that this distance from the optical center C2 to F2 is denoted by small f2 like that. Okay, and let us consider this ray of light is incident at point B. We call this as point B, and its distance from the optical center C2 is denoted by H2. This distance is denoted by H2. Further, this ray of light has suffered the deviation delta 2, such that this angle and this angle, they both will be equal, that is delta 2, like that. Now what would happen if we talk about length L1, then deviation produced, that is delta 1. So I am writing here for length L1, what we have tangent of delta 1, that will be equal to H1 over F1. I am writing here tangent of delta 1, that will be equals to, that is approximately equals to delta 1, and delta 1 is equals to H1 over F1. In this way we can write, let it be equation number 1. Now for length L2, what could happen for length L2? This ray of light falling on it is suffering the refraction and is getting focused at the principal focus, that is the focus of the lens L2 denoted by F2. So here in this case, for lens L2, what we get for lens L2, what we have tangent of delta 2 approximately equals to delta 2, it will be equals to H2 over this distance, this over this, or we can write H2 over F2. Okay, so let it be equation number, instead here we can also write it like as delta 1 is equals to H1 over F1. Now we can write this equation 1. Or here we can write delta 2 is equals to H2 over F2. Let it be equation number 2. Okay. Now, if we consider that F is the focal length of the combination of this length system, let us consider here we have the equivalent length. The optical center is denoted by C, and this equivalent length is forming the image at the same point as is found by the combination of the lenses. Then this small f will be the distance of, or we can say the focal length of the equivalent length. Under that condition, the net deviation suffered by the ray of light will be given by this ray of light. If we extend it further, then we can get the net deviation produced. We will reproduce it in the backward direction here in this way. So we got the net deviation, that is delta. So here I am writing, if f is the focal length, f is the focal length of the combination of two lenses, then net deviation delta will be equals to delta 1 plus delta 2, or we write it in further. Then tangent of angle delta will be approximately equals to delta, and delta will be equals to this distance, and this, let us consider this is DC, so DC is equals to AC1. This distance, that is tangent of angle delta, net deviation produced will be given by this CD, that is equals to H1 over F. So we can write here, that is H1 over F. Now, the net deviation delta can be written as delta 1 plus delta 2. So, if delta is equal to delta 1 plus delta 2, then putting the values, what we get, let this be equation number 3. So, what we get here, so which implies H1 over F is equals to H1 over F1 plus H2 over F2 in this way. Let this be equation number 4. Now, in the next step, what we will do, here we have to put the value of this H2. So how we can put this value? Here in this case, as we look at the diagram carefully, then we see that the triangle AC1F1, this triangle AC1F1 is similar to the triangle BC2 and F2, BC2 and F2. As the triangle AC1F1 is similar to the triangle BC2F2, then what we have, the ratio of sides are equal. Again we will make use of the lower class property. So here I am writing, as the triangles AC1F1 and triangle BC2F2 are similar. So if the triangles are similar, then the ratio of sides must be equal. So ratio of sides must be equal, then we can say, therefore AC1 over C1F1 must be equals to BC2 over C2F2. And substituting the corresponding values, what we get, AC1 is equals to H1 over C1F1. This C1 F1 is denoted by F1. F1 is equals to BC2. BC2 is H2 and C2 F2 is the F2. So I am writing here H2 over F2. Now if I replace this F2, I can write this in terms of F1. Then how we can write this in terms of this? So this distance F2 can be written as, how we can write this? That is, this distance F2 we can write, or H2 distance will be equals to, H2 will be equals to, we can write it as F1 minus D. If I put it F1 minus D, then what would happen? So here in this case, again look at the figure, this distance we want to find F2, and this F2 will be equals to, this F2 distance will be equals to this distance F2 will be equals to, if I want to write it in terms of this, then D minus F. Then we will put the value of here, that is H2. How we can put the value of this F2? Okay, here in this case, we people will take the triangles, right angle triangles, that is AC1 F1 and triangle BC2 F1. Okay, so here instead of taking the triangle BC2 F2, we will take the triangle BC2 and F1. Then what we get? AC1 over C1 F1 will be equals to BC2 over C2 F1. C2 F1. So what we got the value in the next step? What about C2 F1? I require this distance C2 F1. So C2 F1 will be equals to F1 minus D. If I subtract this distance from this distance, then we got the C2 F1. So here we will put C2 F1, that is equals to F1 minus D, or we got the value here, that is, which implies H2 is equals to F1 minus D over F1 into H1. Let this be equation number 5. Now we will put the value of this H2 here in this equation number 4. So what we get in the next step? That is, therefore, substituting the value of, here we will write substituting value of H2 in equation number 4. Value of H2 in equation number 4. What we get? That is, equation number 4, we get H1 over F is equal to H1 over F1 plus H2 over F2. So instead of H2, we will write this value F1 minus D over F1, and this F2 will get multiplied and H1 will remain ahead. That is, I am writing here the value of this H2, F1 minus D over F1 into H1 and multiplied by 1 by F2, that is 1 by F2. So we got the value here, that is H1 over F1 plus what we get in the next step, that is F1 minus D over F1 into F2 into H1. Now look at here, that is H1 on the left hand side and H1 on the right hand side. They both will get cancelled out, and finally what we get, which implies 1 by F is equal to 1 by F1 plus F1 minus D over F1 into F2. Or in the next step we can write it as, which implies 1 by F is equals to 1 by F1 plus F1 over F1 into F2 by breaking this fraction, minus D over F1 into F2. Here this F1 and F1 will get cancelled out, and what we get in the next step, that is 1 by F is equals to 1 by F1 plus 1 by F2 minus D over F1 into F2. So here we have derived the formula for the net focal length of the combination of the two lenses when they are separated by small distance D. Now in terms of power we can write this formula as, or we can write reciprocal of the focal length, that is power. If P is the net power of this combination of the two lenses separated by the distance D, then P is equal to P1 plus P2 minus D into 1 over F1, that is P1 into P2. So in this way, this is the required formula of the net power produced by the combination of the two lenses when they are separated by the small distance D. So this is the required expression for the power. Again I am repeating here. Power. Reciprocal of the focal length of the lens is called power. Or we have defined it that tangent of the angle by which the rays of light are converging or gets diverged after falling through this lens, that is what we call its power. So in order to derive the expression, here we have considered the two lenses L1 and L2 having the different focal length F1 and F2. Let us consider these two lenses are separated by the distance small d. Now what would happen? A ray of light coming from the distant object falls on the lens L1 and get refracted as shown in the figure. Here this ray of light is getting refracted and meets the principal axis at point F1, and F1 is called the principal focus of lens L1. Here in this case, now we have not considered this presence of lens L2, simply we have considered this lens L1. So for lens L1, what we have, the deviation suffered by this ray of light, let us consider it is deviated by an angle delta 1. So this angle and this angle will be same. So under this condition, what would happen? Tangent of delta 1 will be equal to H1 over this F1. We have given that equation number 1. In the second case, if we consider the presence of lens L2 at a distance small d from the lens L1, then again the ray of light falling on this lens L2 will suffer the refraction and get refracted at the principal focus F2. Okay, so now what about its power? That is, or we can say tangent of angle delta 2, that will be equals to H2 over F2, where F2 is the focal length of this lens L2. So we have given that delta 2 is equals to H2 over F2, equation number 2. After that, we have considered that, let us consider the equivalent length, the combination of these two lenses, that is what we call equivalent length, or we can say the combination of the length produces the net deviation delta. Okay? So if F is the focal length of the combination of the two lenses, then tangent of angle delta is approximately equal to delta, and that will be equal to H1 over F. Why I have written this? Because ray of light, if we have considered the equivalent length here, then this ray of light will fall here and will suffer the refraction, and finally it will get focused at this focus, and this distance from C, optical center C of that imaginary combination of the lens, that is In this way, we have considered, we have imagined this combination of the lens produces the net refraction at this point such that its focal length is denoted by f. So under that condition, tangent of delta will be equals to h1 over f. Why? Because CD will be equals to AC1 and AC1 is equals to h1. Okay. Now the net deviation can be written as sum of the deviation produced by the length L1 and L2. Because this net deviation is the deviation produced by the equivalent length, or that is the combination of these two lenses. So we have written there simply values h1 over f is h1 over f1 plus h2 over f2, given it as equation number 4. Now I want to introduce here h1. So I have to eliminate this h2. In order to eliminate this h2, what we will do, we have considered here the two right angles triangles, that is AC1F1 and second right angle triangle. Instead of BC2F2, we have considered BC2F1. BC2F1. Again I am saying BC2F1. So here BC2F1, both the triangles are similar, so the ratio of their sides must be equal. So ratio of sides, that is AC1 divided by this C1F1, it must be equals to BC2 divided by C2F1 in this way. Now what about AC1? This is equals to H1. C1F1 is the focal length of the first lens, that is F1, and BC2 is H2, and C2F1 is we don't have the value of this distance, so we can express in terms of difference between F1 and D, so F1 minus D. So here we got the value of H2. H2 is equals to F1 minus D over F1 into H1. Now as we have calculated the value of H2, we will substitute this value in equation number 4. And as we put this value in equation number 4, we come here, we got this equation. Now H1 will throughout, it will get cancelled out, and we got the formula 1 over F is equals to 1 over F1 plus this F1 minus D over F1 into F2. Now breaking the fraction, we can write it like that, where F1 and F1 will get cancelled out, and we got the net formula. We have got here the two formulas, that is in terms of focal length, in terms of power. So our main aim is to derive the expression for the power of two lenses when separated by the distance d. So this is the required expression. P is equal to P1 plus P2 minus D into P1 into P2. Okay. So this formula you have to keep in mind while solving the numerical problems. In competitions the questions may be there. Okay. Now next thing we people are going to study today is, that is Newton's formula. Newton's formula, what does it say and how we can prove this? Let's study about it. So let's study about the Newton's formula. What is Newton's formula? That is, the question may be asked like that: prove that f square is equals to x1 into x2. So Newton's formula, according to Newton, if an object is placed at a distance x1 from the, let us consider this is our lens. Now lens have the two principal focuses. As we know that this is the optical center of the lens. Let us consider this is the first principal focus, and here it is the second principal focus. So if an object is placed object is placed at a distance x1 from the first principal focus of the equiconvex lens, that is this, then its image is formed at a distance x2 from the second principal focus. I am writing these letters somewhat in larger font so that it is clearly visible to you. According to Newton, if an object is placed at a distance x1 from the first principal focus of the lens, then its image will be formed at a distance x2 from the second principal focus of lens. So here we have considered equiconvex lens, so the focal length is denoted by f. So here we can write in statement form, that is according to Newton, if an object is placed at a distance x1 from the first principal focus of a lens, then its image will be formed at a distance x2 from the second principal focus, of the lens in this. So we want to prove this formula. So here we have considered a convex lens having the focal length f. So let us consider an object is placed at a distance x1 from the first principal focus of this convex lens such that its image is formed at a distance x2 from the second principal focus of this lens. So here what we can write, that is, here in this case, as object distance, we can apply the length equation. What is the formula for the length equation? As we have the length equation, minus 1 by u plus 1 by v is equals to 1 by f. So here in this case, if we consider at equation number 1, so here we have the object distance u is equals to minus of this x1 plus f, and v, that is the image distance, is denoted by x2 plus f. So therefore from equation 1, what we get? Minus 1 over u, minus of x1 plus f1 plus 1 over v, that is x2 plus f, is equals to f. Okay, so here negative and negative sign, they both will get cancelled out, and we get in the denominator, that is x1 plus f1 into x2 plus f. Simply instead of f1 we are writing here f. So what we get after cross multiplying f, x2 plus f, and here plus x1 plus f is equals to 1 by f, like that. Okay. So in the next step, what we got in the numerator, what we get, that is 1 by f is equals to x1 plus x2, and f will get added up. So I am writing here x1 plus x2 plus 2f divided by, on multiplying this x1, first of all we will multiply this x1 with whole this term and then f with this. So what we get? x1 x2 plus x1f plus x2f plus f square in this way, or what we get in the next step, which implies 1 by f is equals to x1 plus x2 plus twice of f divided by x1 into, here we have written, x1 x2 plus x2 into f plus f square. In this way we can write. Now we will do the cross multiplication, so which implies x1 x2 plus x1 plus x2 into f plus f square is equals to, on multiplying this, here I have multiplied this whole term by 1, so here multiplying this whole term by f, what we get, x1f plus x2f plus 2f square. Here again on the right hand side we are taking the common x1 plus x2 and f plus 2f square, or in the next step we can write it as x1 plus x2 plus x1 plus x2 into f plus f square, and this is equals to x1 plus, if I take this x1 plus x2 in this side, then what we get, and minus x1 plus x2 into f is equals to 2f square. So what would happen, this term and this term, they both will get cancelled out. Now in the next step, taking this f square on the right hand side, so we can write here, which implies 2f square minus f square is equals to, this is I think x1 x2. So here we have this term, that is x1 product of these distances, x1 and x2. Okay, now it's clear. And here we got x1 x2. So 2 minus 1, that is 1. Or we got here the final result. I am writing here with the red color, that is f square is equals to x1 into x2. So this is the required result, what we call it as Newton's formula. This is the Newton formula, that is f square is equals to x1 plus x1 into x2. That is square of the focal length of the lens is equal to the product of the distances, that is object distance from the first principal focus and the image distance from the second principal focus. So in this way, students, we have studied about this Newton's formula. Once again I am repeating, we have the Newton formula, f square is equals to x1 to x2, is used in the numerical problems. So according to Newton, if an object is placed at a distance x1 from the first principal focus of a lens, then its image will be formed at a distance x2 from the second principal focus of the lens. So here we have considered a convex lens of focal length f, and an object is placed at a distance of x1 from its first principal focus such that its image is formed at a distance x2 from the second principal focus. So taking the length equation initially, both sides we know that the length equation minus 1 by u plus 1 by v is equal to 1 by f, let it be equation number 1, and here we have the object distance denoted by x1 plus f, that is measured to be in the direction opposite to the incident ray coming from the object, so that's why I have taken here negative sign, and the final image, this is the image distance, so it is denoted by x2 plus f. For the sake of simplicity, here we can write this distance as u, and u, that's why it is equals to x1 plus f, and this distance is called as v, and v is equals to this x2 plus f. So substituting this value of u and v in equation 1, we got this equation. Here negative and negative will get cancelled out, taking LCM by multiplying both these terms and cross multiplying both these, we get this equation. Okay, in the next step, solving this, we get f square is equals to x1 to x2, which is the required Newton's formula and used for the numerical problems. Later on we will solve in the class. Okay. or you can do the practice at your home. If you find any difficulty, then you may consult with me in future. So this is all about the Newton's formula. So till now we people have studied about the power of length, then we had derived the expression for the equivalent power of the combination of the two lenses separated by the small distance d, and then this Newton's formula. Okay. The next thing which we people are going to study is, that is the last topic of this subchapter, what we say, spherical aberrations. What are the spherical aberrations and how we can minimize these spherical aberrations? Let us study about this. Sometimes this question is asked carrying 2 marks in the annual examination. Let us study about this spherical aberration. We people are going to study, that is spherical aberrations. Spherical aberrations, how we can define them and what are the various methods to minimize these spherical aberrations. Spherical aberrations, both are the inability of lens of large aperture to bring the rays of light after refraction to its principal focus. That is what we call spherical aberration. Once again I am repeating. The inability of a lens of large aperture to bring the rays of light to its principal focus after refraction is known as spherical aberration. Means these spherical aberrations are the kind of defect which arises in the lens which are of large aperture. So first of all I am drawing here diagram, then I will write its statement. Here in this case, let us consider a convex lens of large aperture in this way. So the rays of light, some rays of light are traveling close to the principal axis, and these rays of light are known as, what we say, these as paraxial rays. What we call them as paraxial rays. And the other rays of light traveling at a distance, certain distance from the principal axis, are called as marginal rays. These rays are called as marginal rays because they are lying at a margin from the principal axis. So what could happen when the lenses of large aperture are made up of? Then these lenses, they loses the ability to focus these all the wide beam of rays of light at its principal focus. In this case, if this lens is of large aperture, then what could happen? For these paraxial and these marginal rays, there will be 2 principal focuses at which the rays of light after refraction will get focused and the image formed will be blurred. Or we can say, this is a kind of defect. Spherical aberrations are kinds of defects which arises in the lens of large aperture. So after refraction, what would happen? These paraxial rays, I am naming these rays as, these rays are called as paraxial rays, and these rays, these are called as marginal rays, lying at a distance away from the principal axis. These are called as marginal rays. So what would happen here? These marginal rays gets focused relatively closer than the what we can say paraxial rays in this way. So we can say this distance is called as the focal length for the marginal rays, and the paraxial rays, they get focused on the principal axis at a distance greater than the point where the marginal rays has been gets focused in this way. So this distance is called as the focal length for the paraxial rays and is denoted by Fp. This is Fp and this is Fm. That is, this point will act as principal focus for the marginal rays, and this will act as the principal focus for the paraxial rays. So, in this way, we are getting the two focus here. The rays of light are getting focused at 2 points. So, the person will not be able to see the image clearly. So, that's why this defect arises in the lens of large aperture, and we can define it now in the clear way. That is spherical aberrations. How we can define? That is, it is the inability of a lens of large aperture. It is the inability of a lens of large aperture to bring the rays of light. Inability of a lens of large aperture to bring the rays of light of a wide beam, rays of light of a wide beam to its principal focus. The inability of a lens of large aperture to bring the rays of light of a wide beam to its principal focus, that is what we call spherical aberrations. And here in this case we have already illustrated it. So now the difference between these two focal lengths, that is Fp minus Fm, is called as longitudinal spherical aberrations. So here we can write this longitudinal aberration, that is spherical aberration. It will be given by Fp minus Fm. So this, in this way we can define this spherical aberration. Now, what are the methods to reduce these spherical aberrations? What are the methods to reduce these spherical aberrations? So we have the different methods. The first method is either by blocking these paraxial rays or by blocking the marginal rays, by placing the opaque screen stops in front of the lens, so such that only either the paraxial rays or the marginal rays are allowed to pass through the lens, such that there exists only one principal focus, such that the image formed by the lens should be only at one principal focus. Only under that condition we can minimize. So first method is either allowing the paraxial rays or allowing the marginal rays to pass through this lens of large aperture by making use of opaque screen stops. So here we can write by using opaque screen stops, which either allows opaque screen stops in front of lens. I can say in front of lens, which allows either paraxial or marginal rays to pass through the lens, So the first method is by using opaque screen stops. Opaque screen stops may be of the kind of, we can say, cardboard. Small stops are placed here in this way. So only the either paraxial or marginal rays can pass. So the second method here we are going to discuss is, that is by using the two plano-convex lenses. By using two plano-convex lenses, and by placing them apart at a distance equals to the difference in their focal length, focal length. Okay, so in this way, these are the two methods. Another method is same, by using the two plano-convex lenses and placing in such a way that their curved faces lie only in the one direction. For example, this is the plano and this is the convex. Plano-convex lens in this way, and by placing them in the way that their curved faces lies along the same direction. So this will be the third method, but here the two methods are sufficient. The question is asked carrying 2 marks, one for the definition, one for the definition, 1 mark for the definition and elaboration, and 1 mark for the method to reduce the sphericalization. So in this way, your second subchapter, that is the refraction of light, has been finished. So now it's time to solve some numericals based upon this chapter. I'm going to solve here one of the exercise questions, and rest of the questions examples are there from your NCERT book. You can try it yourself, and if you have any doubt, then you can consult with me. So let us move ahead. Okay. Here people are going to solve one of your book exercise question. The question is, in the old books it's 9.38, exercise question is here. Exercise 9.38 in the old books, and new books it is 9.32. The question is, figure shows an equiconvex lens of refractive index. We have given the refractive index of this glass, that mu is equals to 1.50. It is placed in contact with the liquid layer on the top of the plane mirror. A small needle with a strip on the principal axis is moved along the axis until its inverted image is found at the position of the needle. Distance of the needle from the lens is measured to be 45 centimeter. The distance is given to us 45 centimeter. That is the net focal length we have given. Liquid is removed and experiment is repeated. The new distance is measured to be F1 is equals to 30 centimeter. What is the refractive index of liquid? This is the refractive index of glass is given to us. We have to find the refractive index of liquid in this way. So let's solve this numerical. The numerical is, if we understand this diagrammatically, so what we have given here. So we people have given here a convex lens in this way. It is placed on the convex lens, it is placed on the plane mirror, and the liquid is placed in between the plane mirror and this convex lens, like in this way. So we have given this distance. First of all, our needle is clamped over the stand and the parallax is removed, means to say when the tip of the needle joins with one another. So this distance is found to be 45 centimeter. This distance is found to be 45 centimeter, like that. This is the first case. So, and what about in the case number 2? In case 2, we people are given that whenever the liquid is removed, and again the needle is moved and the parallax is removed, under that condition, in this way, liquid is removed now and the lens is placed. Now the distance of the needle comes out to be, this distance is given to us, that is what we call 30 centimeter. Now the parallax is removed at a distance of 30 centimeter in this way. This is 30 centimeter. Now here, in the first case, we people are given the net focal length, that is the needle here in this case at a point where the parallax is removed. Parallax means when the tip of the needle joins with its real image. So at this distance, the parallax is removed and this distance is found to be 45 centimeter. And in the second case, when the needle is lowered from the what we can say clamp stand where it is mounted, so this needle parallax is removed at a distance of 30 centimeter. So this distance is called as the focal length of convex lens. This distance is called as the focal length of the combination of this convex lens, this plane mirror, and this liquid lens. Liquid lens is looking like plano-concave lens. So we have to find the refractive index of this liquid. This refractive index is given. So in order to find the refractive index of liquid, we have already studied about the formula. We have studied the formula F is equals to mu minus 1 into 1 over R1 minus 1 over R2. Okay, so we need to calculate this thing. So in order to calculate this thing, first of all, I must have knowledge about this R1 and this R2. And if we have the knowledge about this R1 and the R2, then we can find this focal length. So first of all, I have to calculate the focal length of this liquid length. Then in the second step, I have to calculate this R, and then in the third step, by using and putting the values of F and R, we can calculate this mu. So let's start solving this. So first of all, here I am going to make some considerations. What are the considerations here? That is, what about this capital F, what about this F1, and what about this F2? So let F is equals to the total focal length of the combination of the lens and the plane. Total focal length of the combination of lenses, convex lens, plano concave lens and plane mirror. So I am mentioning here all the things, combination of focal length of combination of convex lens, comma plane mirror, or simply I can write liquid lens, that is plano concave lens and plane mirror. So here I have mentioned this is the net focal length. Now what about this f1? We have considered f1 is the focal length of this only convex lens. f1 is the focal length of convex lens. Simultaneously a mirror is there, as a result of which we people are able to see its real image. Focal length of convex lens, and we can say plane mirror. And then what about f2? f2 is the focal length of plano concave lens, that is liquid lens. Okay, so let's study here the first case. Now, as the net focal length 1 by f can be given by combination of the focal length of convex lens, combination of the focal length of this f2, that is plano concave, and focal length of this mirror. Focal length of the plane mirror is given to be, as we know it is infinite, so 1 over infinity will be 0, 1 over f, that is we have given this 1 over f, that is given to us 40. So substituting the value, what we get, which implies 1 over 45 is equals to 1 over 30 plus 1 over f2 plus 1 over infinity. So what we get, 1 by f2 is equals to 1 over 45 minus 1 over 30, or what we get here in the next step, 30 here, 45 here, like that, and in the denominator it will be 45 multiplied by 30. So on solving it, what we get, 1 by f2 is equals to minus of 15 over 45 into 30. So 15 3 ja this, which implies f2 is equals to minus 33 ja 90 centimeters. So f2 is coming out to be negative, which means that it is the focal length of this plano concave lens. Okay. We have calculated f2. Now it's time to calculate the radius of curvature of this plano concave lens. Then we can calculate this refractive index mu. Okay, so in the next step, we people are going to calculate the what we can say radius of curvature. How we can calculate it? Well, as we know that for length, we can say for length L1, for length L1, I am writing here, for length L1, what we have, 1 over F1 is equals to A mu G minus 1, that is the refracting index of glass, minus 1 into 1 over R1 minus 1 over R2 according to lens maker's formula. Okay, so here in this case A mu G, it is given to us. We people are not provided with this R1 and R2, but we have the value of F1. Putting the value here, what we get in the next step? What we get here in the next step, which implies 1 over F1. 1 over F1 is equals to 1 by 30 is equals to A mu G, that is 1.50 minus 1 into 1 over R1. Now what about R1 and what about R2? We have already considered while driving the lens equation, that is lens maker formula. This lens is bounded by the two surfaces xp1y and xp2y. So xp1y के लिए what we can say, xp1y के लिए R1 will lie here, and for xp2y the R2 will lie here. So this distance will be measured as positive and this distance will be negative. So here I am writing first of all, here F1 is equals to, we have given 30 centimeter, A mu G is already given to us, that is equals to 1.50, and R1 is taken to be, since it is equiconvex length, so R1 is taken to be plus R and R2 is taken to be minus R. So putting the value, what we get, 1 by 30 is equals to A mu G, that is 1.50 minus 1 into 1 over R1, that is 1 over R, minus 1 over R2, that is minus R. So what we get in the next step, that is 1 by 30 is equal to 0.5, and here 1 by R minus plus 1 by R, that is 2 by R, that is 0.5, and inside what we get, 2 by R is equals to 1 by 30, or in the next step 5 to 10, so 1.0, so we can say that R comes out to be 30 centimeter. This is the radius of curvature of the equiconvex lens. Now here, as we know that here the liquid plano-concave lens is formed, so we need to calculate its refractive index. We know the value of its focal length. We know the value of this radius of curvature. Why? Because the radius of curvature of this equiconvex lens and the radius of curvature of this plano-concave lens will found to be same. So now here I am writing for lens L2. For lens L2, what would happen? For lens L2, for lens L2, for lens L2, what we have, I am writing here 1 over F2 is equals to A mu L minus 1 into 1 over R1 minus 1 over R2. Now here we have the value of F2. F2 is equals to how much? Already we have calculated, minus 90 centimeter. R and A mu L we want to calculate. What about the value of R1? What about the value of R2? Value of R1 will be here. Since here this is the object and this is the image, so this is our plano-concave lens, so it is bounded by the two surfaces again, x P1 by x P2 y. So here this is x1 and this is x2, so here we can say this is R1 and this is R2. So for this lens, R1 is taken to be negative and R2 is taken to be positive. So here I am writing R1 is equals to minus R and R2 is equals to infinity. Why? Because this combination, this plano-concave lens, for this plano-concave lens, this surface is plane, so for the plane surface, R2 is found to be infinity. So putting these values, what we get, that is 1 over minus 90 centimeter is equals to A mu L minus 1 into 1 over R1, that is 1 over minus R minus 1 over infinity, 1 by infinity 0, this negative sign and this negative sign. They both will get cancelled out. So what we get in the next step, 1 by 90 is equals to A mu L minus 1 into 1 over R, that is 30 centimeters. So I am writing here the value. This negative sign and this negative sign, again I am saying they both will get cancelled out. So 33 jar, if I look at here, then what we get, if I take this here, so what we get, 30 by 90, that is, or simply dividing it by 31 is 30, 33 jar 90, so what we get, 1 by 3 is equals to A mu L minus 1. So on solving it, what we get, which implies A mu L is equals to 1 by 3 minus 1 by 3 plus 1, that is equals to 4 by 3, and that is equals to 1.33. So here in this question we get the refractive index of the liquid, therefore A mu L is equals to 1.33. So this is the required answer, and so many times this question is asked in the previous exams carrying 3 marks. In this way we have to solve. This is the last question of this ray optics exercise 9.38 in old books, and new books it is 9.32. Okay. The next popular question based upon this topic we have studied is that sometimes you people are given the numerical, that is length of certain focal length is immersed inside the liquid of known refractive index. Then what about the changing focal length, and what about the focal length of the lens when it is immersed inside the liquid? And this question is asked in the competitive exams. So how we can solve that? I am going to write here the formula for it. So let's study about the formula. So here the topic is comparison of focal length of lens, comparison of focal length of a lens immersed in water, comparison of focal length of lens immersed in water with lens in air. So many times the numerical is asked in the competitive exam. So let us solve it. Let us consider the focal length of the lens in air is denoted by FA. So according to lens maker's formula, we have the formula 1 by FA is equals to A mu G minus 1 into 1 over R1 minus 1 over R2. When the lens is in air, so we have the formula. Here I am writing when lens is in air. So the rays of light will go from air to glass. So that's why I have written here A mu G. Let it be equation number 1. In the second case, when the lens is immersed in the liquid, then what would happen? Then 1 over FL will be equals to, now on immersing the lens in the liquid, मान लो ये हमारे पास lens है, let us consider we have the lens, convex lens, it is surrounded by the liquid, then the rays of light will go from liquid to glass. So instead of writing here A mu G, I will write liquid to glass L mu G minus 1 into 1 over R1 minus 1 over R2. Let this be equation number 2 in this way. Now we want to compare the focal length of the lens immersed in water with the lens in air. So we will divide this equation number 2 by 1. So dividing equation 2 by equation 1, what we get? 1 over dividing equation 2 by 1. Instead we will write dividing equation 1 by 2. 1 by equation 2. Then what we get? 1 over FA. Why here I am dividing 1 by 2? Because we want to compare the focal length of the lens immersed in water. So FL should be in the numerator. So that's why 1 over FA over 1 over FL will be equals to 1 over FA, that is A mu G minus 1 into 1 over R1 minus 1 over R2 divided by L mu G minus 1 into 1 over R1 minus 1 over R2. So what we get here, this 1 over R1 minus 1 over R2 will get cancelled out, and here in the left hand side, this denominator will become numerator. So what we get in the next step, that is FL over FA will be equals to A mu G minus 1 over L mu G minus 1 in this way. So this is the required formula, and we can further elaborate it. But this L mu G is the relative refractive index of the glass with respect to liquid. So we can write L mu G as A mu G over A mu L. So if I put its value here, then this formula will further get expanded up. A mu G minus 1 over A mu G over A mu L minus 1 in this way, and is equals to FL over FA, or in the next step we can write this formula as A mu G minus 1 over A mu G minus, taking the LCM A mu L and multiplying it A mu L over A mu L. So this formula again will be expanded like that, A mu G minus 1, and if I multiply it with the numerator, then what we get on rearranging this equation, what we get? A mu G minus A mu L. So this is the required formula to compare the focal length of the lens immersed in the liquid of non-refractive index with the focal length of the lens in air. Very important formula. It is asked in the competitive exam so many times, and in the annual exam carrying 3 marks numerical problem. So this is the comparison of focal length of the lens immersed in water with the lens in the air. Sometimes the question may be like that, ki find the change in focal length of the lens. The change in focal length of the lens, if we want to calculate, then we have to multiply this FA by this whole term by solving it, and then we will calculate the delta F. That delta F will be equal to FA minus FL. So accordingly we can find the answer. The next popular question which we are going to study here now is based upon the similar concept. If a convex lens is immersed inside a liquid of same refractive index, greater refractive index or smaller refractive index, then how the lens will behave? Either it will behave like a plain glass, either it will behave like a convex glass, or it will behave like a concave lens. Let's study about that type, and it is also asked in your previous year's exam in CBSE. So let's study about it. Here we have behavior of lens in different, what we can say, different mediums. So how we can say here? I am considering here the case, that is the first one. Here I am taking the lens, convex lens, and here the case is, that is, this convex lens is immersed in the liquid, that is liquid having the refractive index A mu L, and this is the A mu G, and the condition is given to us. What would happen if A mu L is equals to A mu G? Under that condition, what would happen? In the second case, here in this case, A mu L, refractive index of the liquid is greater than refractive index of glass. And in the third case, if the refractive index of the liquid is smaller than the refractive index of glass. So in all these three cases, what would happen? Here we are considering refractive index of liquid is equals to refractive index of glass. This glass is placed in the liquid of refractive index A mu L. Then what would happen? How it will behave? This is the liquid. Let us consider. This is the liquid in this way. So here what we can say? Here in this case, if A mu L is equals to A mu G, then we have already derived here the formula for the behavior of liquid in this. So if both the refractive indexes are equal, under that condition the lens will behave like plain glass, or we can say the rays of light falling on it will goes unrefracted. And this is the case similar when a magician immerses a piece of glass inside a liquid which is taken in the glass, and that piece of glass disappears due to this phenomenon, because under that condition that refractive index of both the materials are found to be same, and they behave like plain glass, and it gets disappeared when it goes inside the glass. Here in this case, what would happen if A mu L is greater than A mu G? Under that condition, this lens will behave like the diverging lens, or we can say it will behave like a concave lens. This lens will behave like a diverging lens. And if here in this case it is possessing the original property, that is refractive index of glass is greater than the refractive index of the liquid, then it will possess this original property, that is it will behave like a converging lens, that is convex lens. Now the question rises here, why it has happened. So right now we have derived the formula. What we have the formula, that is FL over FA is equals to A mu G minus 1 into A mu L over here we have written. What was the formula? We can derive it in the way, that is 1 over FA is equals to A mu G minus 1 into 1 over R1 minus 1 by R2. And here in the liquid, what was the formula? L mu G minus 1 into 1 over R1 minus 1 over R2. So what was happening here? Dividing this equation 1 by 2, what we get? FL over FA. We have divided this equation by this. So A mu G minus 1 over L mu G minus 1 was coming out, or then on solving it further, what we get? A mu G minus 1, and in the denominator, what was A mu G? A mu G over A mu L, and here A mu L was there. So on the basis of this, we can find that whether the lenses behave like plain glass, or the diverging glass, or the converging glass. Look at the first case there. If refractive index of both the liquids are found to be same, so this difference will become equal to 0. If this difference is 0, then Fn, focal length of the lens in the liquid, that will become infinite, and focal length of the focal length is infinite for the lens for the, what we can say, glass lens, plain glass. The focal length is found to be infinite, that's why it will behave like a plain glass, Why? Because its focal length is found to be infinite. Here in this case, second case, if the AMUL is greater than AMUG, AMUL is greater than, sorry, here we are writing AMUL. If AMUL is greater than AMUG, AMUL is greater than AMUG, then this difference will be negative, and if this difference is negative, then focal length of the lens will be negative, and the focal length is negative for the concave lens, so that's why it is behaving like the diverging lens. It will behave like diverging lens. Why? Because here in this case the focal length is found to be, focal length of the lens in liquid is found to be negative. Here in this case, what would happen? He is saying that AMUG is greater than AMUL, means to say refractive index of the liquid, that is the medium in which it is placed, is found to be smaller than the AMUG, the refractive index of glass. Then this difference will be positive, and focal length of the lens in the liquid or in that particular medium will be positive, and focal length is positive for the converging lens. So that's why here this lens will behave like converging lens, because its focal length is found to be positive. So in this way, the question is asked in the previous years, carrying 3 marks. The similar question is there. You have to solve, that is, what would happen for the same conditions if we have placed a concave lens for the same conditions. It is also asked in the other sets in the previous year examination. So this formula is quite helpful for you people in order to solve this type of questions. So this is all about the behavior of lens in different mediums. Okay. Now next thing we people are going to study, that is, what is the relation between refractive index and the wavelength of the light. Refractive index and the wavelength. So here I would like to introduce the formula, that is Cauchy's formula. What about this Cauchy's formula? The relation between, this thing should be kept in mind, relation between refractive index and wavelength of light. Refractive index and wavelength of light. So this relation is popularly known as Cauchy's formula, C-A-U-C-H-Y, Cauchy's formula, and the Cauchy's formula is named so because the scientist called Cauchy has given this formula. No need to go for the derivation, simply we have to keep in mind refractive index of the medium is equals to A plus B over lambda square plus C over lambda raised power 4, where A, B and C are known as constants, and lambda is called as the wavelength of light used. So from this relation, what we conclude that refractive index of the medium is inversely proportional to the wavelength, that is square of the wavelength of light used. In this way, this Cauchy's formula is there. So here we conclude mu is inversely proportional to lambda, means to say greater is the wavelength of light used, smaller will be the refractive index. Now what is the relation between refractive index and the focal length? So here we have already used as the length maker formula 1 by f is equals to mu minus 1 into 1 over r1 minus 1 over r2. So according to this formula, what we conclude that mu is found to be inversely proportional to f. So if greater wavelength light is used under that condition, what would happen? Smaller will be the refractive index. If refractive index is smaller, then the focal length of the lens will be greater. Or we can also write f is inversely proportional to mu. Smaller is the value of the refractive index, greater will be the value of the focal length. So in this way, this is the competitive question, that is sometimes whenever the violet light is replaced by the red light, then what would be the impact on the focal length of the lens? This type of question is asked in this current session, the examination which has been taken place for the 12th class. So in this way we have to do. Okay, so in this way we have finished this subchapter 2. Now it's time to start a new subchapter, that is what we call dispersion of light. So students, here in this case, dispersion of light, last year the CBSE has eliminated the topics like rainbow, defects of vision, and the topic what do you mean by dispersion of light, dispersive power, angular dispersion. So these 2-3 topics has been eliminated from the syllabus, from this dispersion of light subchapter. So here we have to only deal with the questions or the derivations which includes just like minimum deviation, maximum deviation, condition for no emergence, condition for grazing, angle of incidence. In this way, these conditions we have to find. So let us study about this second subchapter, that is dispersion of light through the prism. Okay. Here in this third subchapter of ray optics, we people first of all will study about that what is prism. What about the prism? If somebody asks you that define prism, then how we can define this word? So how we can define prism? Simply we call is a portion of transparent refracting medium bounded by the two surfaces inclined to each other. So we can define this word, that is, it is a portion of transparent refracting medium, transparent refractive medium bounded by the transparent refracting medium. It is a portion of transparent refracting medium bounded by two surfaces. What about surfaces? Plane surfaces, I will write. Bounded by the two plane surfaces inclined to each other, bounded by the two plane surfaces inclined to each other, inclined to each other in this way. It is a portion of transparent refracting medium bounded by the two plane surfaces inclined to each other at a certain angle. At a certain angle, we can also add here, at certain angle. At the certain angles. That is what we call prism. Here, how we can explain it diagrammatically? Let us consider the two plane surfaces like as is bounded by the two plane surfaces. Here in this case, this is the first one plane surface and this is the second one in this way. So again I am drawing it. It is the portion of transparent refracting medium bounded by the two plane surfaces inclined to each other at a certain angle in this way. So this is the first surface, this is the plane surface, this is the second surface, or we can draw it like this. I am shading it, and this angle, this is what we call angle of prism, and here this edge is called as refracting edge. This edge is called as refracting edge, refracting edge. And these are the two refracting surfaces, plane refracting surfaces are there. We will write these are the plane refracting surfaces, plane refracting surfaces in this. And what about this angle? This angle is called as angle of prism, angle of prism, and this prism is made up of material of refractive index mu. In this way, we can define this word: portion of transparent refracting medium bounded by the two plane surfaces inclined to each other at a certain angle, and that angle is called as angle of prism. In this way, we can define this word. Okay. Now let's come to the main question which the CBSE asked in the previous years. That is, prove that delta plus A is equals to I plus E. Okay. The question is, prove that delta plus A, that is deviation plus angle of prism, is equals to sum of angle of incidence and angle of emergence. 3 mark question is this derivation. Again I am saying we have to prove sum of angle of deviation and prism is equals to the sum of angle of incidence and angle of emergence. So in order to prove this relation, first of all we have to draw a diagram. How is the diagram? And this relation we are going to prove for the prism having the angle of prism greater than 10 degree, greater than 10 degree. So let us consider a prism which is made up of, I am considering here the first part. Okay, so here we have considered the prism. Let us consider an equilateral triangular prism made up of material of refractive index mu is placed in the ray medium. So what would happen? A ray of light incident on this face AB of the prism at an angle of incidence. This ray of light is incident PQ. We need the angle of incidence. So in order to find the angle of incidence, what we do? We draw the normal. We draw the normal on this face AB. This is the normal. Okay. And what would happen? It will give us the angle of incidence. Now, a ray of light when suffers the refraction, as it is going from optically rarer to denser medium, so it suffers the refraction and goes like that. Let us consider this angle is the angle of refraction, that is the R1. Now, as this ray of light is incident on face AC, then what would happen? Again, in order to find the angle of refraction R2 or angle of emergence, we need to draw another normal. Let us consider this normal is O and dash. Now, a ray of light as it goes from denser to rarer, it will move away from the normal. And let us consider this angle is angle of emergence and this angle is the angle of refraction, what we say R2. Okay. Now, how much deviation this ray of light has suffered in order to prove this result? What we will do, we will reproduce these rays of light, this in the forward direction and this emergent ray in the backward direction. At a point where these two rays of light intersect each other, let us consider that point is denoted as T, and T is, here we got the angle of deviation, that is delta. Let us consider the angle of prism is denoted by A. Okay. Now let's derive the expression or prove this formula. In the first step, I am going to consider here the quadrilateral, or simply we can say the quadrilateral OAQOR. This incident ray is PQ and the emergent ray, I am naming it as RS. Okay. Now first of all, I am writing here in quadrilateral AQOR. What we have. As you know that sum of the four angles of quadrilateral is found to be 60 degree. So 360 degrees. So how we can write it? That is, in quadrilateral AQOR, the angle of prism A plus angle AQO plus angle QOR plus angle ARO is equals to 360 degrees. Okay, so in the next step, what we get here, that is, since this angle AQO and ARO, these both the angles are of 90 degree. So substituting the value AQO and ARO 90 degree, 90 plus 90, 180 degree, and when we take them toward the right side, we get A plus angle QOR is equals to 180 degree, which implies angle QOR is equals to 180 degree minus A. Let it be question number 1. In the next step, what we will do? Here we people will consider this triangle, that is TQR. In this triangle we need this angle and this angle. Okay, so here we have to prove this relation, that prove that delta plus A is equals to I plus E. Yes.
वो आपने अभी जितना सेशन लिया ना
जी,
का मुझे थोड़ा डिटेल
सेकंड सब चैप्टर खत्म हो गया, मैं प्रेजेंट कर रहा हूँ।
हाँ पर आप लिख देते हैं चैप्टर में जो टॉपिक लिया है वो टॉपिक और कौन से डेट पे कौन से टाइम पे वो जरा लिख के वैसे मुझे व्हाट्सएप स्टूडेंट्स का भेज रहा हूँ ट्रायल बेसिस पे एक बार देख लेते हैं उसको रिप्लाई कर।
ठीक है, तो अभी मैं थोड़ा इसको खत्म कर लेता हूँ।
हाँ ठीक है,
व्हाट्सएप कर दूँ, चलेगा?
व्हाट्सएप कर दीजिए।
ओके।
30 तारीख को 30 तारीख उसका टाइम टॉपिक इसी तरह 31 का।
So here in this case, we have already defined our prism. Prism, that is portion of transparent refracting medium bounded by the two plane surfaces inclined at an angle, certain angle, that is what we call prism. And here now we people are going to prove this relation which is asked in the previous exams, or in this current session it may be asked carrying 3 marks. Prove that delta plus A is equals to I plus E. So here we have considered a prism, equilateral prism, triangular prism ABC, in which the ray of light, this PQ, is made incident at an angle of incidence I. In order to find this angle of incidence, what we have done, we have drawn the normal ON on the face AB. So what would happen, the ray of light after suffering refraction, it goes or it is refracted along QR, and this R1 is called as the angle of refraction R1, and then what would happen, it is made incident on this face AC. So again we have plotted the normal so that we got this R2 and then angle of emergence E. Okay, so first step we have taken in quadrilateral AQORs, as we know that sum of all the angles of the quadrilateral is found to be 360 degree, and here on this face AB and this face AC, this angle AQO and ARO, these angles are perpendicular, so 90 degrees each, that is AQO and ARO. 90 plus 90, 180 degree. When subtracted through 360, what we get, 180 degree, or angle QOR is equals to 180 degree minus A, in this way. Let it be equation number 1. Let's move to the step number 2, that is in triangle TQR. What we say, in triangle TQR we have the exterior angle delta, and it must be equals to, that is angle of deviation, it must be equals to sum of two interior opposite angles. Now if we want to find these angles, then as we know that this angle I and this angle, they both are vertically opposite angles, and if I subtract R1 from this I, then I will get this angle, that is what we say, that is I minus R1. On the same way, this angle of emergence and this angle is, they both will be equal because they are vertically opposite. On subtracting this R2, we got this angle, that is what we call E minus R2. Angle of emergence E minus R2. So considering this triangle TQR, we have the angle of deviation delta, that is exterior angle, is equal to sum of two interior opposite angles, that is TQR plus angle TRQ. So angle TQR is I minus R1 plus E minus R2, or we can write I plus E minus sign taking common R1 plus R2, and this is delta. So in the next step, let it be equation number 2. Okay. In the next step, we people are going to take this triangle, that is QOR, and by making use of angle sum property, as angle sum property is sum of the three angles of the triangle is equals to 180 degree. So by making use of that property, we will calculate the value of R1 and R2, and we will put here in this equation. So let's write in triangle OQR, what we have, that is R1 plus R2 plus angle QOR. QOR is equals to 180 degree, which implies angle QOR is equals to 180 degree minus R1 plus R2. In this way, let it be equation number 3. Now, from equation 1 and 3, what we conclude from equation 1 and 3, what we get? 180 degree minus A is equals to 180 degree minus R1 plus R2. Okay. So in the next step, this 180 degree will get cancelled out, or we can say which implies A is equals to R1 plus R2. Let this be equation number 4. Okay. Now from equation 2 and 4, what we get? Putting the value of this R1 plus R2 in equation number 2. So now from equation 2 and 4, what we get? Delta is equals to I plus E minus A, or which implies, the final result which we have to prove, delta plus A is equals to I plus E. So in this way we have proved the result, that is the delta plus A is equal to I plus E for the prisms which have the angle of prism greater than 10 degrees. And later on the next session will be continued, this topic will be continued further. So this is all about the derivation, and one thing should be noted here, on what factors this deviation suffered by the ray of light depends. It depends upon 3 factors. Number 1, the wavelength of the light used, which wavelength of the light is you are using. The second thing, the material by which this prism is made up of. And the third thing, that is the angle of prism, whether it is greater than 10 degree, whether it is lesser than 10 degree. So 3 factors which determine the deviation suffered by the ray of light. Once again repeating, number 1, wavelength of light used. Number 2, material with which this prism is made up of, whether it is made up of flint glass, whether it is made up of what we can say, flint glass or other glass, that is crown glass. And the third one is depends upon the angle of prism. Thank you.